Time to finalize this lecture by talking about spectroscopy. All right, so just a couple things I want to remind you about. The first thing is that we're going to be looking at mass spec in addition to infrared spectroscopy and NMR to determine the structure of molecules. You've done some of this already in previous assignments, uh, but let's start with the mass spec. So what you basically want to remember is that the base mass, the M plus mass, is ultimately what's going to tell you whether or not nitrogen may or may not be present. If the M plus value happens to be an odd value, you will have an odd number of nitrogens. If the M plus value is even, you will have an even number of nitrogens. And even we're treating 0 as being an even number under this premise. So if the molar mass, the M plus value, is even, that could very well mean that there's no nitrogen at all in the molecule, right? But if you do make the claim that nitrogen is going to be present, then you have no choice. You'll have to start at least with 2. Beyond that, it'll have to be 4 or 6, right? It will have to be an even number. All right. The other thing is that the M plus plus 1 peak is the one you're going to use exclusively to determine the content of carbon. Whatever the abundance of the M plus plus 1 peak is, you're going to divide that by 1.1 to get the number of carbons present in the molecule. If you do have an M plus plus 2 peak, this is going to tell you whether chlorine, bromine, or sulfur are present. And the way to basically tell is that the abundance of that peak has to be a multiple of 33 if you have chlorine, or it has to be a multiple of 100 if it's bromine that you have in the molecule, or it has to be a multiple of 4 if it's sulfur that you have in the molecule. All right, and then what we do after we determine what the chemical formula is, we calculate the index of hydrogen deficiency, which is basically determining the number of hydrogens that a regular alkane would have. You basically multiply the number of carbons by 2, and you add 2 to that, so 2m plus 2, to determine the total number of hydrogens, the maximum number of hydrogens. And you subtract from that the equivalent number of hydrogens that are present in the actual molecule. And the equivalency of hydrogen is that all the hydrogens in the molecule, you count them. If you have halogens in the molecule, you count them as if they were hydrogen. If you have oxygen or sulfur, you simply ignore them from the point of view of hydrogen. But if you have nitrogen or phosphorus, you subtract 1 hydrogen for every nitrogen or phosphorus that the molecule contains. And at the end, you divide that whole thing by 2 to tell you the index of hydrogen deficiency. Okay, so that's from the mass spec point of view. Then from the NMR point of view, the proton NMR, just to kind of remind you, if you have carboxylic acids, they will tend to fall between 12 and 14 ppm. If you have aldehydes, they'll fall between 10 and 11 ppm. Aromatics, which is kind of the big topic here, will fall between 7 and 8 ppm. But I want to be very clear about this. You will have a peak between 7 and 8 ppm, roughly speaking, if and only if there's an actual CH bond on the aromatic ring. Because if it happens to be the case that you have substituents on all of the carbons of the benzene ring, then you don't have a CH. And so you shouldn't expect to see a peak at 7 or 8. And that doesn't mean that the compound is not aromatic. It just means that you don't have a CH on the aromatic ring. So it's something to keep in mind. Peaks around 5 and 6 are your alkenes, right? 3 to 4, take this with a grain of salt. Sometimes that's where the alcohol show up, but I've seen them show up pretty much anywhere on the spectrum, depending on the concentration, density, even temperature and solvent, being used. The amines, tend to fall around 2 and 3, but also kind of like the alcohols tend to move about a little bit more. Alkynes 2 to 3, and then your alkanes 0 to 2, just to give you an idea, right? So an example of this, right? Let's say that we did the mass spec, right? And then from that, we determined that we have a molecule that has 10 carbons, 14 hydrogens, and 2 oxygens. The index of hydrogen deficiency basically would be as follows. We first determine how many equivalent hydrogens this will have, right? The oxygens we totally ignore. We have 2 in the formula, but doesn't matter as far as the hydrogen count. We have no nitrogen, so there's no need to worry about them. And then we have 14 hydrogens, right? So we'll just count the 14 hydrogens as the equivalent hydrogens in the molecule. And then the total number of hydrogens is based on the 2n plus 2 calculation, where n is the number of carbons. So if we simply plug in 10 for n, this will tell us that we have 22 hydrogens max that could be in this molecule. All right, so then what we do is we plug in the numbers, right? 22 is the max, the 2n plus 2 value, minus the 14 equivalent hydrogens that are present in the actual molecule. And then we divide that by 2. So 14 minus 22 minus 14 is 8, divided by 2 is 4. And the point of this is to kind of show you that when you hit this value of 4, or maybe higher, it is very, very likely that you have a benzene ring. It's not absolute proof that you have it, but it's very suggestive of it. So that's one thing that you want to notice with the index of hydrogen deficiency. Then, same compound, the one that has 10 carbons, 14 hydrogens, 2 oxygens. When you look at the spectrum, if it is a benzene ring you probably will have peaks between 1600 and 1400, which are correlated to the carbon-carbon bonds of the benzene ring, specifically the stretchings. So that's something you might notice in the infrared spectrum. Now, the other thing to also pay attention to is this region that I'm highlighting in the box, right? Because double bonds, aside from the aromatic double bonds, will tend to fall between 16 and 17. And as you'll see later on in this class, even 1800, right? So from 16 to 1800, that's where the double bonds will fall. Carbon-oxygen double bonds in particular, 17 to 1800, that tends to be the place where they fall. Carbon-carbon double bonds, non-aromatic, will fall, between 16 and 17, generally speaking. And the triple bonds fall between 21 and 2300. So the fact that there's not a lot of stuff happening right here means that we probably don't have any of those things happening. But we do have these peaks at the 15, 14, which kind of like tells you that maybe an aromatic is present in there. But further corroboration of that would be that if you look at the region around 3000, we do have, mind you, kind of small peak, but we do have a peak showing up a little above 3000, which is an indication that a CH bond on an sp2 hybridized carbon is actually present. And that will kind of tell you, okay, well, IHTO4, sp2 hybridized carbon bound to hydrogen, a benzene rings that's seeming kind of likely to be here. All right, so in my opinion, as nice as that is, the proton NMR is going to be, in most cases, your most conclusive, way of telling whether an aromatic ring is present or not. And it's just by looking at where the peaks fall. Notice that this peak falls very close to 7 ppm. It's a little bit on the low side for this molecule, but that's because of the functional groups that are also present there. But it's close enough that you can basically say, yeah, okay, that looks like an aromatic set of carbons. And also the integration, 4 hydrogens integrate to this singlet. You could definitely have 4 hydrogens on a benzene ring, no problem. So that looks indicative of aromaticity. Now, additionally, we have these other 2 peaks, proton peaks, right? One of them is a quartet, 4 hydrogens. One of them is a triplet, 6 hydrogens. This combo, right? If you look at the ratio, this is a 2 to 3 ratio for the integrations. And this combo of quartet to triplet, 2 protons of a quartet for 3 protons of a triplet, this is literally the signature of an ethyl group specifically, right? Because for this peak to be a quartet means that you must have 3 neighboring hydrogens, as in a methyl group. And for this other peak to be a triplet means that you must have 2 neighboring hydrogens next to you, as in a CH2. So if you combine those 2 things together, CH2 and CH3, that's an ethyl group. Now, on top of that, notice that we haven't addressed the oxygens yet, right? Well, that has to do with this quartet peak, because this quartet peak falls around 4 ppm. And we already established that this is a quartet because next to you, you have a CH3. But because this is 2 H's for every 3 H's, this is a CH2 that happens to be next to a CH3, right? The ethyl substituent in essence. But the CH2, which is what this peak is ultimately, appears at 4 ppm, which is way too far downfield on the spectrum for it to just be a regular alkane carbon. So what this is basically telling you is that this CH2 must be attached to one of the oxygens, right? Because attachment to an electronegative element such as oxygen will actually have the effect of de-shielding the electrons of those protons substantially, right? And that's something to pay attention to. Don't discount the ppms; they're important. All right, so what basically this will also tell us is that if you look at the integrations, right, we have 4 hydrogens in the aromatic region. That means that out of the 6 carbons of benzene, 2 of them are being occupied by substituents, right? Otherwise, you will have more than 4 hydrogens that are aromatic. Now, the other thing about it too is that this is a single peak. And the only way you're going to get a single peak like this is if all 4 hydrogens are equivalent to each other, all 4 aromatic hydrogens. So take that into account and consider the fact that this is not 2 to 3, but 4 to 6. What this is telling us is that we have 2 groups, 2 ethyl groups, which the CH2 is still bound to oxygen. So we actually have 2 ethoxy groups present in the molecule. And if we want to ensure that these 4 hydrogens are pretty much equivalent to each other, and then we introduce the 2 ethoxy groups. The only way to really make this happen, right? So ethyl groups, we already talked about that, is to kind of deal with the symmetry of the molecule. Now, one more thing I'll tell you before I show you the symmetry of the molecule. Notice that the carbon NMR has only 4 peaks, which means that you only have 4 inequivalent carbons. Now, out of those 4, the ones that fall above 100 are going to be your aromatic carbons. And notice that you only have 2 non-equivalent aromatic carbons. And at the same time, you have 2 non-aromatic carbons that are inequivalent, right? So 4 inequivalent carbons in total. The protons have to be, associated with each other. So these 2 on the right side must be the ones associated with the ethyl group, and these 2 are the aromatic, right? So all of that together, what should tell you is that you have 2 ethoxy groups. You have to have 4 hydrogens of the benzene ring that are equivalent to each other. The only way for that to work out is if the ethoxy groups are directly across from each other in a para position, because then you'll see that this H up here is next to an ethoxy, is next to another CH. But you could say the same thing about this one. This CH is next to an ethoxy, is next to another CH. This CH right here is next to an ethoxy, is next to another CH, and this CH is next to an ethoxy, next to a CH. So all 4 of those hydrogens are indeed equivalent. All right, so this will be kind of the investigation you want to keep in mind. So I'll stop the video right here and I'll catch you on the next lecture. Bye-bye.